Welcome back everyone to the lecture about applied parameter analysis. This week is about spot detection and tracking, and I'm happy that I can use some material from Jean-Yves Tinvet, Tobias Pietsch, and Florian Jug. What is tracking? Tracking itself is actually a discipline in science which is pretty old, several decades. Researchers are already working on that. It's basically following objects. So it's an active research field. There's a lot of applications. You see here on the right. It's a pretty older video, but I think Konrad from the ETH Zurich that I can show it here. Tracking objects, cars, people, I mean anything. And as again, people are working on that already for quite some time. It's active research is ongoing because it's the computational effort behind is pretty high. So it's not like a simple for loop which does some detection of objects and then plots that in a table. In order to follow several objects which are going in different ways, and I mean that's from a computational point of view, from an algorithmic point of view behind, quite complicated. So we will not talk about how to track cars and people and whatever in natural images. We will more talk about how to track cells in microscopic images. From a bioimage analysis point of view, typical goals are measuring track properties like speed and velocity and to understand spatial temporal relationships between cells. I mean, one of these relationships kind of obvious, right? It's a cell division, for example. There is a relation between cells in space and time. And we would like to understand that from a scientific point of view. We would like to understand that better. We would like to know which biological, physical properties in the background play a role here. And therefore, we need analysis, image analysis, in order to have quantitative information about the process, which is ongoing. A typical visualization of what tracking is, you see here. So tracking as a process of analyzing data consists basically of two steps. One step is image segmentation, or one step can be image segmentation. So for example, we have two time points, time point 1, time point 2, and we segment all objects in these time points. That's what you did earlier with the yeast cells, right? And then we match these objects to each other. And this is something we didn't do with the yeast cells. So we want to know the object in image number 1 corresponds to which object in image number 2. So that's matching. And I will come back to this a bit more in detail later on. So we have two time points, for example. It's a very short movie. So potentially, of course, there are more time points in the future. And if we look at that in a more general way, we always have kind of time point t, time point t minus 1, time point t plus 1, and we have kind of a concatenation of several images where there always has to be a matching to do in between them. And from an algorithmic point of view, the whole process consisting of segmentation and matching together is super easy to do from a programming point of view, and we get that, for example, to something like 99% correct. So we can have that. That's technically feasible. However, when we concatenate these time points over time, we run a bit into trouble. So, for example, let's assume we have 1,000 objects in 500 time points. How many decisions do we have to make in order to have a correct tracking completely with all segmentations and with all matching steps in between? So we have something like 500 million decisions to make. If from one time point to another, 99% are correct, so that's what we just said, and we have 100 time points, then the likelihood that we have or the probability that we have the correct lineage is like something like 0.99 to the power of 99. That means we have, with 100 time points, we have a likelihood of having the whole tracking over all these time points correct of something like 37%. And if we talk about 500 time points, it goes down to 0.07%. So this is kind of error accumulation over time, or error propagation over time. So this is an issue. So that means tracking is a super hard problem from a technical point of view, and this is why active research is still ongoing. A 0.5% improvement from one time point to another is kind of an extreme improvement over a whole movie when you track cells or when you track objects. And there are different things which can go wrong during tracking. So for example, if you think about segmentation, that's where we were before, we can, for example, miss objects, or we can misinterpret the image in a way that the number of images is wrong. So here you see an example on the left and on the right side, different potential solutions to the same image. So are we looking at one cell, or are we looking at two cells? That might be hard to see, and also for a computer super hard to differentiate, right? But if we look at several images over time, it is, at least for us human and maybe also for the computer, easier to see the difference and easier to process this image. So we have here a video, and when you play this video, you actually see that was the time point. That these were two cells. They were just moving by each other after dividing. So and that may not be easy to spot from this one particular image. It might be easy to spot from the whole movie. So that's under segmentation. We miss something, and there's also over segmentation. So how many cells are these? Is it like 3 or 2, 3 or 1? And we also have a video for this one. Yeah. And here you see that this particular cell is obviously really like one cell. It may divide later on in a later time point, but it hasn't done yet. So that's why if we do this in a wrong way, like on the left side, we would have an over segmentation in this particular case. And furthermore, just about terminology. So far, I was mentioning segmentation and matching. So I mean, segmentation and matching is kind of obvious over different time points. We have a segmented object, or we have multiple segmented objects over time. And we would like to match them to each other, and we would like to know, for example, if the shape of this object is changing, then we have to do a segmentation for every time point in order to determine the shape change over time. And matching these objects from one time point to another, knowing which object in frame number 1 corresponds to the other to any other object in frame number 2. That's matching. And there's also spot detection and linking. So if we do not do segmentation is like an outline, a binary image. That's the result of a segmentation. If we only have a coordinate, only if we have a point, and no outline, no volume, no area, then we talk about spot detection. I will show a little bit more in detail what it means on the next slides. And if we use spot detection for tracking, so if we have spot positions in frame number 1 and spot positions in frame number 2, and we now want to know which is the the optimal connection of these spots to each other to have an optimal linking, then we do linking. So that's the difference between segmentation and matching and spot detection and linking. Both are common, both are used, and dependent on your particular use case, you will go the one or the other way. In general, I would say typically spot detection is easier because you don't have to have such an immense perfect precision compared to outlining an object. It's simpler from a computational point of view. That's why faster, easier to get, usually in many of the use cases. So what does spot detection mean in a bit more in detail? So we look here at an image, and I draw a line here through these two nuclei. So we are looking at nuclei in a Drosophila dataset, Drosophila embryo dataset. And I will now plot the signal along this line, and I get a plot out like this. And if we do spot detection, what we do is actually we search for local maxima in this plot or in the whole image. So this is now the plot kind of represents a one-dimensional image. It's just the pixels along the line, but we can also, and we can for sure search for maxima, but we can also search for maxima in a two-dimensional or even three-dimensional image. So, and many algorithms which you can use for spot detection use a term called, sometimes it's threshold, sometimes it's tolerance, or height, also sometimes used. And this is what it means. So when you measure the intensity in the image to the local maximum, right? You will see, okay, it's in this case something like 100, 120. If you enter a tolerance of 120 in these algorithms which ask for such a parameter, it will not tolerate any maxima which are not as far distant from each other as 120. So in simple words, there must, between two maxima, there must be a valley where the lowest point is actually at least 120 away from the maxima. Otherwise, it would not be. Otherwise, the maxima would not be determined or recognized as actual maxima. That's why one particular algorithm where you enter the tolerance of 120 would not see these local maxima as maxima because they are not high enough, or the valley between them is not deep enough. So if you enter, for example, a tolerance of 30, that would mean it would detect these 3 points as maxima in this plot. And if you enter a tolerance of 15, you would have 4 maxima along this line. When you now look in the original image where this plot came from, there is 2 maxima. it's not 4. And that tells you, in this particular case, that you have to enter something like 100, 120 in order to get the spot detection right, that only these bright objects are really marked as the detected thing, right? In Fiji, for example, there's an algorithm called find maxima, where you enter the prominence. I think they recently renamed it. It was tolerance until a year ago, and then they renamed it. They now call it prominence, but it is basically the same parameter, a threshold. And depending on what value you enter, so here I entered 100, and you see that it draws these crosses on top of the objects I would like to recognize it. If I enter 100, something reasonable comes out. If I enter 25, much too many comes out, right? If I enter 50, I come closer to the point. If I enter 100, again, that's approximately the value I would have expected. And if I enter 150, then I lose points. So not all points are determined, are detected anymore, because the valley between these points is not high enough. So there are now two strategies how you can deal with these tools. You can sit there, turn on the preview point selection checkbox, and enter different values that might work immediately. And if you use the same value for all the images you want to process, that should be fine. If it's harder, if you cannot find a good value immediately in a way like this, then it may indeed make sense to draw a line or a couple of lines in your image, draw this plot along the line, and find out, okay, how is actually the image looking like? How are the intensities? And then you may have a better idea of what value to enter here in this particular field. At the end, again, what counts is having a value which processes all of your images, the whole study ideally, also independent from conditions. So if you sit there and you have to, as a human, judge images in front of a screen, unfortunately, with these tools, it's not possible in a different way, right? So if you have to do this anyway, then please blind yourself at least for the conditions under which these images were taken. So if you, for example, have some images taken from a mutant and some images from a control, then ask a colleague of you to take 10 or 10 random images from your study, give them names 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and remove any hint for you as a person looking at the image, what is control, what is mutant. Blind yourself, then you can find out these parameters, because then you are objective. You do not know what is the mutant and what is the control. And ensure that these values are working for a variety of images and not just from control and not just from mutant. And most importantly, do not set different prominence or threshold values for different conditions. That's actually quite decisive. This strategy is quite powerful. You can do spot detection in images which are impossible to segment. So there are ways of dealing with issues like that. And if you still, if you still cannot manage to find a good spot detection result for a particular image, you may want to process some filters in advance, right? And when we did thresholding, did some Gaussian blur in advance, so you can also do that here, but there is an advanced technique I would like to introduce you today, because it is then later on in the future, it's quite important actually. So let's start from an original image and we apply a Gaussian blur to it. For example, with a sigma of 2. So that means, and we do noise removal, right? Then we apply another Gaussian blur filter to the original image with a larger sigma. So it could also be something like 20. So it's like really like a lot. And that information of the image is really going away. And this is the so-called background image. If we now subtract the one from the other, we get a so-called difference of Gaussian out, a DOG, a dog image. And this is actually, when you think about what we are doing here, we apply two filters to one image and then we subtract the one from the other. It is actually, when you think about it, it's actually something like we do noise removal and background subtraction in one shot. So this is what Gaussian blur does. Yeah. And it's often the question is, okay, what are good values for the sigma of the one Gaussian blur and the sigma of the other Gaussian blur? These sigma values have something to do with the size of the object you want to detect. So if your object are, for example, something like 5 microns large, then the one sigma should be below 5 microns, because you want to remove all the noise, all the objects which are smaller than 5 microns. And the other sigma must be larger, because the background subtraction should not remove your object. So it's like you have to be actually in between, kind of. Let's talk about it in a different way. What does this program do? Or if you just, after I finish this sentence, you may click on pause for a second. What kind of comment would you write here instead of step 1, step 2, step 3, step 4? What is this macro doing? Yeah, and I can give you a hint. And this macro is calculating different combinations of sigma values, different DOG images, and saving into a folder. So this here is a screenshot of my Windows Explorer actually showing me all the images which were generated with the script before. Again, it's basically just a reminder. Image analysis or science in a computational manner is not just writing code, it's also about reading code. So in case somebody comes with such a script and the script's not working, you may want to be able to read it and find out what it's doing in order to fix it for your particular project. And here you see, depending on, so first of all, if I set sigma 1 and sigma 2, these two sigmas for the two Gaussian blurs, if I set them to the same value, like 1 and 1, and then I subtract the one from the other, I get an image out where there are only zeros in. Yeah? So that does not make much sense. And it also happens with 7 and 7 and 10 and 10, so it's kind of obvious. If I subtract an image blurred with a sigma of 1, and I subtract from that an image with a sigma 4, I get an image out like this. And it still looks similar to the original image. We just see these black rings around our white objects. And when we go further in this direction, by increasing this 1 sigma, the image kind of becomes more similar, but also a bit more blurry compared to the original image. If we go in the other direction, like subtracting a sigma 4 image from a sigma 1, it is actually inverted. So this is actually the inverted version of this one. And if we now go further in this dimension, it's like, if you do spot detection, it may be super hard here in this case on this image, because it may still find a lot of noise spots as actual spots in your image. It might be optimal at some point when you apply spot detection to this image, you may get actually quite good result out. At some point, the blobs here in this image are fusing, because the two sigma values you entered are blurring the image so much that actually the detail is lost. The detail of the objects you want to see is going away because you blurred out of your image. And at some point you can really not differentiate it anymore. So what I'm saying here is that the spot detection on an image like this may not succeed anymore in a proper spot detection result. So the best combination of two sigmas for this particular image may lie somewhere here in this center area. And if you, for example, are confronted to a program where difference of Gaussian is a term, right? And you can always take your original image to the difference of Gaussian yourself, for example, by writing a little macro which subtracts the one blur from another. And you can play a bit with it to understand what it's doing. I'm saying that because sometimes you see software where difference of Gaussian is mentioned and you should enter two sigma values. And many people, including myself, some years ago, didn't know what you actually have to enter here. And then we are trying random things out. It may work at some point, but it's actually better to understand what these filters are doing, because then you can actually be just faster in answering the question the program asks you. And there's another interesting filter related to that. So first of all, let's introduce the Laplace filter. So the Laplace filter is the so-called second derivative of a Gaussian blur. I'm also not so much a math person, right? So you see here a Gaussian distribution plotted in a diagram. So, and the second derivative means that we actually from every point to every point, let's assume there are points along this line, we measure the gradient and we plot the gradient from the left to the right. So the first derivative, the gradient along this line, looks like that. And if we now make the derivative, we measure the gradient along that line and plot in a new plot, we get that out. And so this is when you look at it actually, so it's like a Mexican hat. Looking from the side basically. So this is the tip of the head, and these two spots like are sitting lower. So this is the that's why the Mexican the Laplace filter is called the Mexican head filter, and it makes a bit more sense when you look at that in 2 dimensions. So let's assume we do this with an image, and we have now, that's basically a 1-dimensional image expressed as a 2-dimensional image. It's a kind of transition thing. I hope it helps. So you have a black image with a white line. If we now apply a Gaussian blur to it with a sigma in x and no sigma in y, or sigma 0 in y direction, we get an image out like that. So this basically, this plot here from the left to the right corresponds to the intensity here from the left to the right, right? And if we form the first derivative of that, we get this one out. Let me just move myself to the side. And if we calculate the first derivative of that, we get that split out. So it's bright here, so it's high, and it's dark here, so it's low, and it's gray and left and on the right side. It's same value, basically almost the same values here on the left and on the right side. And the second derivative looks like that. And now we do this not just in x direction, but also in y direction. So we start at a point and we apply a Gaussian blur to it. So this is what you have seen something like 4 weeks ago, earlier in ImageShade. You were able to do this yourself. If you take the first derivative in 2 dimensions from such an image, you get that out. And again, when you go from the left to right, it's gray, brighter, gray, dark. So it's like exactly still as the plot here. From the top to the bottom, it's the same thing. Gray, bright, dark, gray. So it's the same plot. And if you do this in 2 dimensions, it looks like this. And now it's basically you're looking from the bottom into the Mexican hat. And that's why it's dark inside and bright outside on the front, right? So this is the so-called Mexican hat filter. And depending on the situation you want to do something with it, it may be very helpful. It has actually a very similar purpose like the DOG, and that's why we also often call it the LOG, the Laplacian of Gaussian. So first of all, little repetition. How is this operator called? And what is this matrix here? Think about it. Yeah. So we convolve this image with a kernel matrix. And this, when you look at these numbers here, it's high in the middle and low outside, and around it, it's basically gray. So we are looking into a Mexican hat. So this is the Laplace filter expressed as a kernel matrix. And when you take this image and you convolve it with this kernel matrix, you get that image out. And you may say, okay, what do I do with that? So that's the Laplacian of the original image. If we blur our original image with a Gaussian blur and then apply a Laplacian of it, that's the Laplacian of Gaussian, the LOG, we get an image out which is similar to the DOG. It shows our images, our objects in the image a bit better, so we can likely better, easier, with a higher precision, with a higher quality, segment this image or do spot detection in this image. And the contrast, so the background actually becomes kind of more even. So this is what Laplacian of Gaussian is doing for us. Okay, so we have now spot detection. We also improved the spot detection with difference of Gaussian and Laplacian of Gaussian, and now we want to do linking or matching. And when you look at various objects over time, so for example, we have 3 images, at time point 1, at time point 2, and time point 3, and we see 2 objects in each of this image. We have now potential solutions to this problem, how to link these objects to each other. So this would be the one solution, and this would be the other solution. And we can, just from looking at these 3 images, we cannot really say. It's possible that these 2 nuclei bumped into each other and then go again in the other direction, but it's also possible that these 2 nuclei were flying by each other and did not touch and are just continuing their trajectory. So you cannot really know. This is actually a hard case, I would say. And that's why it's not always just I look for this one object in time point number 1 for the object which is the closest in time point number 2. So it's often not as easy as that. And if you have problems of that kind, you have several different solutions which describe the scene. I mean, that's different solutions of the same scene. Both are possible. Both are maybe similarly likely. And if you have these different solutions, and you have to bring these solutions to a point where you make a decision on the optimal solution, which you now finally take as the linking result, we are calling this situation a so-called linear assignment problem, LAP. And finding the solution with the minimal costs is a computational, quite complicated problem. And I will not go deeper into algorithms doing that. But you should know that this is what is expensive kind of when the computer does the processing of a data set for tracking. Some terminology, when you look at the so-called lineage tree. So this is now, for example, from the left to the right is time. And we have at the beginning, we have a cell. The cell is dividing into 2 cells at some time point. And then these 2 cells are also dividing into the future. And what we finally have, and we observed all this correctly, we have a so-called lineage tree. And computer scientists also call this thing a graph. in TrackMate, in a software which I will introduce soon, and you will then see later a bit more in detail, a software called TrackMate. One of these arms, but also the whole graph itself is called a track. So it's like, it's not, I would not say that it's a term which is internationally defined, but at least you should know for this particular software what a track is. Furthermore, if you go from one node in time, so if you go from one time point where they are dividing to the next time point, that's an edge. And I already mentioned it, that the points in a graph where things are splitting, when there's like things meeting or splitting, merging or splitting, these are nodes, or in some softwares also called spots. And when you think about not spot detection, but segmentation, it could be a segment or a labeled object. When the graph ends at some point, so you have you go from the left to the right, it splits more and more and more. The endpoints of this graph are called a leaf, and if the endpoints are called a leaf, then the starting point can be called the root. And that's it with the terminology and with the basics of tracking. The next very short lecture part will be about cell tracking with TrackMate. See you soon.